Okay, good morning. Today we're going to talk about z-scores and the standard normal curve. As you are aware, the standard z-score is calculated by an observation minus the average divided by the standard deviation, right? And so if we have an observation that is, say, 3 minus an average that is 2 divided by 1.5, then calculating a z-score is relatively easy. 3 minus 2 is equal to 1. 1 divided by 1, let me put it down here. 1 divided by 1.5 is equal to 0.66. And that's relatively easy to calculate, but what does it really mean? What do we mean when we talk about the z-scores and all of that jazz? So if we have a normal distribution, something that looks kind of like that, and we know that the mean is 0, and here we're not talking about the normal, we're talking about the standard normal. And a standard normal distribution is a little different because it has a mean, a mu of 0, and it is a perfect curve. This clearly is not a perfect curve. Let me see if I can draw that again. Let me give you a higher quality curve here. All right, let's try again. That's a little better. That is not a little better. Anyway, when our mu is equal to 0 and we have a standard normal curve, then negative 1 sigma is exactly 1.0. Negative 2 sigma is exactly 2.0. Negative 3 sigma is 3.0, and so forth. 1, 2, and 3. 1, 2, 3. A standard normal curve has a mu of 0 and a sigma of 1. And why do we do a standard normal curve? Man, that's really bugging me. Let me see if I can fix that. Ugh. Why do we do a standard normal curve? We do a standard normal curve because I can't measure the probabilities and the percentages when I don't have a standard normal curve. However, if I were to turn around and say, well, what is the probability that x is, say, less than 1 or less than negative 1, right? I can ask that question because I can go to 1 and I can say, hey, look, what is all the area under the curve? What is that? That is calculable when I turn around and use a z-table. Ta-da! This is from the internet, ztable.com. You have this in your book. Whatever stats class you're taking, whatever stats book you have, I promise you have one of these probably on the inside cover. And in this case, if I go to negative 1.0, which is here, and 0, which is here, then I know that the answer is 0.1587. Again, 0.1587 right here in the middle. So I'm going to pull that over, and I know that the area under the curve is equal to 0.1587, or 15.87%, right? So what is the percentage under the curve left of 1.0? 15.87. Okay, you're going to do a bunch of these. Now, this chapter, next chapter, you're going to do tons and tons of these, so get ready. But more to the point, how does a z statistic come into play? Well, when we have a distribution of any kind that is not standard, we might have a normal curve where the average, let's say we're talking about shoe sizes, and the average shoe size is, I don't know, 9. And the sigma is equal to 1.5. Well, we still have a normal distribution. We still have a normal distribution. This is 9, sigma, 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 sigma. But I don't have a 0 here. And so I need to draw another one in parallel down here that looks, well, that doesn't look anything like that. That looks kind of like the one above it. And we say, it still doesn't look anything like that. But you get the point. I am here for my math, not for my drawing skills. This is 0. So this is a standard normal curve. And this guy is your regular normal curve. So this is my shoes. And then this guy is, say, my stats or my unique table, my zero table, right? Where the mu is equal to 0 and the sigma is equal to 1. Ba, 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 ba. All right, so the real question is, if I have a shoe size of, say, 7, that puts me about here somewhere, más o menos. If I have a shoe size of 7, what is the area under the curve left of 7? I have no idea. And if I were to go back and do this by hand, I'd be doing some calculus, I'd be doing all this other stuff. I'd have to evaluate the standards between the blah, blah, blah. I don't want to do any of that stuff. So some poor grad student way back when was tasked to figure out what the area of the curve looks like here at some number, right? Let's call this z, or z sub 1 or z sub 7. Or, whatever, let's just don't worry about that. And say, hey, look, I don't know what this is, right? But I do know what this is. On the standard normal curve, I know what this number looks like. So how do I get from here to here? Well, what I have to do is I have to do a standard normal conversion. So now I do a z-score or a z-stat or a z-conversion, which is equal to, in this case, x. What's my x? X is 7. 7 minus mu is 9, divided by 1.5, and that is equal to 7 minus 2 is negative 2 over 1.5. Why is it negative? It's negative because here's my mu right in the middle, and I'm on the left-hand side, so it's going to be negative. That makes perfect sense. Let me get some working space here. Negative 2 divided by 1.5 is going to be negative, is going to be negative a z-stat of negative 1.33. So on this board, I know that I am at negative, well, I don't need that one. Let me screw it up a little bit. I know that I am at negative 1.33, and I can measure everything left of whatever this is at negative 1.33. Note that this is also negative 1.33 sigma. Right? I am negative 1.33 sigmas left of 0. Okay, take that into consideration when you're thinking about this stuff. So now I come back to my table. Let me turn this into a snapshot real quick so that we can play with it. Oh, that didn't work. Let me turn this into a snapshot real quick so I can play with it. Full screen snip. Thank you very much. And then bring that over here. Make that bigger. And I'm looking for negative 1.33, which is right about here. Negative 1.3. Oh, but I'm missing a digit. So I'm always going to start on z coming down and then add the hundredths digit here. So this is negative 1.33. I'm going to start here, I'm going to go there, and then I'm going to match these guys up. So this guy's going to go to here until I get to here, and the answer is 0.0918. 0.0918. All right, well, that makes sense. All right, so what is the area under the curve left of here? This is this guy. The area under the curve is 0.0918 or 9.18%. So the answer to our question, more to the point, what is our question? Our question is, what is the percentage of shoe sizes in the population that is size 1.33? Nope, not 1.33. But what is, because I don't care about this, right? 1.33 is some arbitrary number. I care about all the size 7s, right? I care about all the size 7s. So how many shoes in the population are less than a size 7? And the answer is 9.18% of all shoe sizes in this particular population are less than a size 7. What we do when we do this is we are looking at real data in a normal distribution. We're using a z transformation to go from the normal distribution to the standard normal distribution, so we can figure out what the area of the curve looks like, and then we can apply it back to our question at hand. In essence, mathematicians, they don't want to go out and do the hard calculation every time. They want to go out and do easier calculations, and we have developed this table, even though it looks a little confusing, as a shortcut, so to speak, so that we don't have to do the long calculations every time. How do we calculate a z? Well, we did this in chapter 4, or we did this previously. The z is equal to whatever observation I'm interested in minus the average of that one divided by sigma, and we're going to use this to go from the normal distribution through my z to the standard normal distribution.